lecture 7 of our semester. Let's go to our last slide. So in the last slide or last lecture, we have thought about the drift mechanism. So since our electrons and holes, both of them are charged particles, so if we apply, for example, certain electric field, then our electron, which has a negative charge, will be pushed away from that direction, and the hole, which is positively charged, will be drained by that electric field. So here you can see that we have some certain discussions about the direction of their movement. So although we have the same electric field, depending on their charge, so their movement can be in the opposite directions. And the last one we have discussed in a previous lecture was, okay, if we have a constant electric field, then that is corresponding to an acceleration, a constant acceleration. So if we just apply the Newton's second law without any constraint, then it is expected that the speed of our electrons or speed of our holes can increase indefinitely. So here you can see that this is initial velocity, and here we have the term linearly dependent on the time variable. Because it is because we have assumed a constant electric field, so constant acceleration. So if we go to very large time variable, then yes, the value like this, the magnitude of our velocity, the speed, can be quite high. So everybody understand this is not the case. So the speed of electrons or holes, that is just in a certain range and does not exceed, for example, typically say in our system, usually it does not exceed, not that much exceed the values like 10 to the 7 centimeter per second. Of course, we have to understand there are exceptions. Some electrons can move much faster than this value. However, when we consider just the average velocity of our electronic gas at a certain position, then more or less its speed is bounded to this value. Okay, so these two components or these two observations shows clear contradiction. So one is, if we apply certain electric field, then it will be accelerated. Yes, we know it. And the real observation is, however, even though we have the constant electric field, however, its speed cannot exceed a certain value. So that is easily understood by the existence of scattering mechanisms. So the velocity of the carriers does not increase indefinitely under the electric field. So it is because simply they means that the carriers are scattered frequently and lose their momentum. So you understand this one. This figure simply shows certain velocity versus time relation at over a particle. So I'm saying that let's say that usually when we say something, then usually we wanted to consider collections of electrons or collections of holes. There are many holes and many electrons. However, in this graph, we are just looking at the trajectory or time-varying behavior of one particle. So you can see that there is a constant slope of our velocity versus time relation. What is it? This is corresponding to an acceleration. So we can expect that, okay, since it has a linear behavior shown here, so we can say that this is corresponding to a constant acceleration applied to this particle. So if we have just acceleration only, then what we can expect is just indefinitely increasing speed in this way. But here we have introduced a certain stars. There is a certain mysterious effect or event, something called as a scattering event. And after that, so before this event, just before its event, it was there, its speed was so high. However, after this short time instance event, after that suddenly it loses its momentum and its velocity is much more de-accelerated. So what happens here? So simply speaking, it means that there is some interactions between our particle and something else, and it suddenly de-accelerate our electron or hole. So simply speaking, let me just draw once again. Here, for example, if we apply electric field in that way, then our electrons are accelerated. So it is getting faster and faster. However, at a certain position, suddenly its speed becomes quite small. So what happens here? So using only our electric field, we cannot explain its behavior, why it is de-accelerated or sometimes even further accelerated. So this one is related with some other effect other than the electric field, and they are called the source of such kind of acceleration or de-acceleration. They are called scatterers. So there is something which introduce scattering event. So when that happens, so although I have written in that way or drawn in that way, scattering events not always de-accelerate the particle. So sometimes it can even further accelerate the particle. Okay, so anyway, within a short time, it just suddenly changes its momentum value. It means that the particle's momentum value. Of course, we have more frequent or more higher probability to de-accelerate it. So the acceleration happens more or less frequently. However, anyway, there is also possibility to accelerate it. So now you are looking at the trajectory, or not exactly trajectory, or time varying velocity, and without scattering event it will be accelerated. However, by action of this scattering event, it loses its momentum and once again accelerated. After that, once again scattering happens and goes this way. So it's like something like this. Someone is just rolling a ball up to the hill, so it is going, or he is or she is going in that way, but in one's journey something happens and it is just the ball is located at the original position once again, and this guy try to push and push. That happens indefinitely. So let me just make a simple demonstration. Although we have some quantities like velocity, acceleration, or something like that, but the essential point is nothing related with physical number. So I just introduce a normalized game, so which does not include any kind of physical thing. So we have 10 players. 10 players can be 10 human players or any entities that is allowed. And initially each of them has an integer assigned to them, so from -5 to 5. So there they can have how many cases? There can be 11 cases. So that is uniformly distributed. So we can just give any number, so independently. After one time step, to everybody, 1 is added. For example, if my starting value was 4, then after that the number becomes just 5. So after one step further, my number becomes just 6. Then what will happen? Everybody in this room can assume that when we have initial case, what will be the expected average of our velocity? There are 10 players and their numbers are uniformly distributed from -2 to +5. So average will be just 0. You may have +1. I may have -2. So they can have random numbers. However, when we make an average, maybe that will be just 0 because we have introduced a uniform distribution. After one step later, what will happen? Everybody gets just number 1. So we can say that maybe in average everybody the velocity or average of our numbers will be 1 and number 2. So if we go to n steps, then average of our numbers will be just number n. That is corresponding to just Newton's second law. We have accelerated our electrons regardless of their starting velocities. So after some time later, they will get certain increase of their speed or their velocity. So given by unit value times steps. So that will be the case. However, this is not that much interesting to us. In order to understand the action of scattering, we just randomly select a player. So we have 10 players. So randomly select. Okay, I will select this guy, or later this guy, and then the selected player's velocity is again randomly distributed over our initial velocity range from -2 to 5. So what will happen? So 10 of them, okay, we were 10 guys. After that, one step later, 9 of them will gain. I get 1 point. However, one unlucky guy will say, I just lost all of my initial velocity, and I was just randomized. Okay. Then after once again, one step later, also among 10 players, one of them will say, I get another 1 point, and one guy will say that, oh, I'm too unlucky, I lost my velocity. So that will be quite a simple game and nothing related with the exact number like certain kind of acceleration or velocity like that, because velocity is just a normalized number and acceleration is also a normalized number. And what happens? I just land this game many times and just select one realization. So this one is one example of such kind of game. So blue, here you can see that there are blue curves and one red line, and blue curve just shows the trajectory or behavior of 10 players in this game. I did that kind of a play for 500 times. So here the number is 500 times, and you can see that there are 10 different graphs corresponding to 10 different players. So what you can see is velocity of each player can even arrive at number 50 or even here close to 60. What does it mean? How can one player can have a velocity even close to 60? It means that one player was so lucky, so every time among 10 of them one is selected. However, one guy was, oh, I was lucky. He or she was quite lucky, not selected by this random selection for how many times? More than 50 times. He or she survived quite a long time. So this is a very lucky guy. However, although very lucky, but eventually this guy was selected, then what happens? It goes just to drop to the initial range of -5 to 5. This is a good analogy to the behavior of electrons and holes in our electronic system. When we apply certain electric field, it is accelerated. Every particle is accelerated. Oh, I'm so fast, I'm so slow. However, regardless their initial speed, all of them are accelerated, and there is a certain chances to be scattered by external environment. Once it is selected, then it loses almost all of its gained velocity, then go to just slow state, and it goes the same procedure again and again. So that was the observation about our blue lines. Okay, for individual player, life looks like sometimes good and sometimes quite bad. I gain a lot of velocity, wow. However, even for that lucky guy, so life changes quite a lot. But point is, we must consider not this blue trajectory, but we have to consider this red one. Red one is on average of each time instance. So for 10 players, we just took the average every time instance. How does it look like? Can you see certain trends? Okay, starting from almost zero value. Why we have almost zero value? Because that was initially uniformly distributed from -5 to +5. So in average, maybe they will be quite close to 0. After that, you can see certain behavior. How does it look like here? In this phase, you can see that average velocity is increasing. Why? The main mechanism is 9 among 10 gains 1, so that's the reason why it is increasing. After that, it does not increase indefinitely, so here you can see that although it is quite much fluctuating, however, in a long term, how does it look like? Although we have a certain fluctuation, but it is staying around a certain value. Maybe that will be the average value. So maybe you can understand what I'm saying. What I'm saying is, although we have applied a certain acceleration, just introducing small scattering event. So here scattering event is modeled as the random selection of a small portion of a particle and just to randomize its velocity, that introduce such kind of a drastic behavior or drastic difference. If we didn't consider this kind of a random selection, then we know that, everybody know that that will be just to increase like this. So so now you can understand average velocity of each carrier. So the velocity of each carrier shows certain kind of sawtooth-like behavior: scattered, 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 acceleration, scattered, something like that. However, the average velocity shows much smoother transition, and eventually what we can expect is after a certain time later, the average velocity will approach to a steady state value, although it is not perfectly matched to a certain value exactly. However, we can see that, we can expect that its value will just change only around that state, the state value. So you will see so many times such kind of behavior when you just keep studying this kind of disciplines. Then you may say that this is your actual signal, and you can see time, so average of this signal. Then you can say this is the steady state value, and here at every time instance you can measure the difference between your actual value and expected steady state value. So this value is called as what? Called as, yes, this is called as noise. So of course, in our everyday life, when you say that noise, it's a sound. So this is unwanted sound is called as noise. However, in electrical engineering, we just expand this meaning a little bit. Unwanted signal is called as a noise. So then what is noise in this case? Let's just say that this is the expected behavior of our signal. Signal sometimes it can be drain voltage, or sometimes it can be gate voltage, sometimes it can be drain voltage, or many different quantities can be characterized, and we can expect certain value expected from our calculation or measurement by some means, and if there exists some deviation from the expected value, that is called as a noise signal. Okay, so well, anyway, if we understand this one, then now we can see that the average velocity of our electrons or our 10 players, just have a steady state expected steady state value and certain noise signal here, here, or here. Everybody can now understand this kind of behavior. Then, although actually my original major was the noise study, however, at the beginning, most people are interested with its average behavior. Noise is a secondary thing, so for a while, let's consider the average, the behavior of average velocity. Then, how can we expect or estimate final steady state value? So now let's just say that, let's come back our simple example and say that they have the average velocity. There are 10 guys and their velocity is averaged number 10. Then how many points do they have? So their average is V, average velocity, and there are 10. Then if we just collect all points, velocity points out of them, then we can certainly say all of them have in total 10 times average velocity time points. So for example, you have 0 point. Some guy has minus 3 point. So when they have their average becomes just 0.2, it means that since we are 10 people, so the net sum will be just number 2. Quite similarly, we can say that this is one of the situation at a time instance. Then now let's go to the next time instance. Then what will happen? Think about what will happen to this system. Your 9 players will get 1 point each. So from the viewpoint of total amount of points, now you can say that, okay, starting from this number, 9 will get just number 9. Then what will happen? One unlucky guy will completely lose his or her points. So what is the expected loss? Expected loss is just, since we have selected only one guy, so that will be the expected loss. One guy was selected and whose point is just becomes average number 0. So then what we are expecting is, since this is considering the steady state behavior, a time instance and the next time distance, the expected the total amount of a point should be the same. So what I'm saying is, we must say this should be valid. Initial time point at a certain initial time point and next time point. 9 of them gains 0.1 and 1 of them just lose complete the average velocity. So please try to solve this one. If you solve this one, that is too simple, you will find that average velocity becomes just number 9. Then now let's come back to our example. So can you see the behavior of our average velocity? How does it look like? it is not located 20, 30 or 0, but it is just around the number 10. So you can easily understand this kind of a simple estimation can be done with simple steady state approximation. So what we can expect is very simple. Okay, now let's consider the average velocity. At a certain time, they have average velocity. There, the change of average velocity is simply given by, okay, this is corresponding to acceleration. So each electron is accelerated, and some of them are so unlucky, so its velocity is just reduced to 0 when a scattering event happens. So that is described in that way. Starting from a certain time instance t, now we go to t plus delta t, very short time instance. During that time, every electron will be accelerated and only some of unlucky electrons will be scattered, and when it is scattered, then actually it is corresponding to the negative sign here. Why do they have a negative sign? It is because it is related with loss of velocity. Okay, so although we are considering just number 1 or 10 players, maybe you can easily generalize it to, instead of number 1, it can be corresponding to the acceleration, actual acceleration calculated from the magnitude of electric field you have applied. And also, although we are considering just 10 human players, but we can say that it can be generalized to n many electrons or holes inside our electron gas or hole gas. That can be easily understood. So then, by solving this equation, at a certain condition, what is the certain condition? The certain condition of the steady state condition. Then in this steady state condition, the average velocity no longer grows or no longer increase or decrease. So at that condition, we can say average velocity does not change. I'm not saying that average velocity equal to 0. No, but instead of that, I'm saying that the time variation of average velocity is 0. In that case, now we can say the velocity can be just given by minus times q tau n and n and the electric field. This relation can be obtained. So please consider the physical meaning of this average velocity. Although we are now writing it as velocity, but it should be regarded as what? Not a velocity of one electron or one hole. This is just a collection or average velocity of our electronic gas or whole gas. And when we write down in that way, we have already made a certain approximation. What was the approximation? It was the steady state approximation. So the steady state average velocity is proportional to the electric field, and it has certain proportional coefficient. So depending on the situation, this proportional coefficient can be high or low. So we are now saying that this scalar number is written as or called as mobility. So when we solve previous equation, now we have this expression, and that proportional coefficient is called as mobility. So simply speaking, let's consider two cases. There is a particle or a gas whose mobility is so high, and consider another extreme whose mobility is so low. Then what will happen? Although you have applied the same magnitude of electric field into two gases, particles inside this gas will react quite a lot, and they will move quite fastly. And in the case of this low mobility case, although we have applied the same electric field, their speed would be quite low. Okay. The typical range, you must understand this one. Typical range of our mobility inside our silicon is not in the range shown in the textbook. So please have a look at this one. Yes, for example, you can see that in the textbook, electron mobility inside the silicon is around 1300 or 1400 in that case. However, this is not the realistic number. Also, you must understand this is the unit for our mobility. Please remember this unit system. So please remember this number. And in this unit system, we typically say that okay, 1000 or 1400, but this is not achievable in the realistic case. We have much lower. How much lower than that? More than 5 or 6 times lower than this value is only achievable in our electronic devices. So, but it just shows the maximum values, maximum theoretical value we can expect from certain material, not related with the device application, but material itself shows this kind of thing. And when you have a look at this number, yes, it is around anyway 1000. And previously, several years ago, when first graphene was considered as an electronic channel material, so people were really amazed because it shows something like this. Its electronic mobility was reported to 10 to the 6, 1 million square centimeter per volt second. So people were really amazed. So maybe instead of this super high number, for example, you have a certain so-called 3,5 material. So out of this 3,5 material, when you build a transistor, the typical thing you make is called as HEMT, high electron mobility transistor. So why it is called as HEMT? Why it is called as high? It's the device level mobility is really in a range like 1000. So although with silicon we cannot never achieve the level like 1000, however using 3,5 materials we can easily have some thousand or few thousand square centimeter per volt second was easily achievable. So that's the reason why we call it as HEMT. Now everybody can imagine that the impact of this super high number. We were quite happy with 1000. but we are now talking about 1 million. So, but this is also related with the material. If we go to the device, then in order to make a device, we have to introduce certain structures into it, and all of those insertion is related with scattering. So the realistic value cannot be achieved. So in reality, such kind of a high value cannot be achieved. So up to now, I have shown you the maximum value we can imagine. But how about the lowest value we can imagine? In the case of a P MOSFET, we can easily have the numbers like just a few 10 square centimeter per volt second in the P MOSFET. And even in this case, now this is generated from crystalline silicon. When you did your best job, you can get the levels like this. If you have different materials like polysilicon channel, then actually your mobility is even lower. Or if you use certain amorphous materials, of course you have exceptions, but in many cases amorphous materials have even lower mobilities, lower than 1 or 0.1 or 0.01, something like that. So mobility also shows quite high differences when we make a comparison between different materials. However, for a given materials, it has its well-defined range. So silicon, for example, if you just use silicon, then you never expect values like 1 million or 1,000. You have to at best expect several hundred square centimeter per volt second. And if you are working with, for example, polysilicon channel, and if you say I will achieve 100 square centimeter per volt second, then you are actually lying. So please don't play with your mobility. Mobility is extremely difficult to improve. It is easy to degrade it. If you wanted to degrade it, just to do a poor job, then you can get low mobility. It is quite easy, but increasing the mobility is an extremely difficult job. Actually, it is all related with the engineers' job security. So engineers, why they are paid by company? Because they have some capability to keep the mobility level as high as possible. Okay. So anyway, now I'm talking about the electron mobility, and it shows in that way. How about the hole? In the case of a hole system, also we can expect a similar quantities like hole mobility, but please note that in this case we must have different leading coefficient, because in this case, if you apply certain electric field, your hole will follow that direction. So now here you have a positive sign, and here you have a negative sign. This is related with the different polarity of your particles. But except for this sign difference, then we can have just a linear relationship between the electric field and the velocity, magnitude of its velocity. And once again, I wanted to ask you to remember the unit of this mobility. Even some guys graduated from certain ECS department, there are some guys who do not remember this unit system. Please try to remember this unit system. Sometimes you must you must be familiar with numbers. So sometimes you must be good at theory, but at the same time you must be good at numbers. Okay, then so now we can consider the quantity called as current density. So I will spend some time on this concept because it is really important for our future discussion. So now let's consider current density. So sorry about that. I mean that you are right, but what usually people write down in that way, volt second. So it means that actually this is square centimeter volt second. Second is in the lower part, and this one shows that square centimeter is divided by voltage and second. Okay, so in many cases we'll write it down. So how can I say, in reality we must be a little bit careful. We must write down in that way. Okay, so anyway, second should be placed in a lower part in this division. Okay, so so I'm not quite sure whether that is a really long notation. So the best way we can write down would be like this: square centimeter per volt per second. Okay, so thank you for your question, and thank you for your question. And actually, in my opinion, actually, this notation, the frequently adopted notation, shows some ambiguity, because if we have to calculate, so how do you calculate this number? Then do you have any assumption that we must consider the multiplication between 3 and 4 first and takes the division? So usually we if we just follow the rigorous way, then we have to introduce parentheses. However, this one is the usual way we write down: square centimeter per volt second. So please understand, this is a typical one. Yes. Now we go to the concept of current density. In my opinion, actually this is quite important. So please, if we study the electronic circuit or microelectronics or something like that, we typically have the quantities like a terminal current. For example, if we have a transistor, then transistor, we frequently assume that drain current or source current, gate current, we say in that way. We say a current labeled with a certain terminal. So if you have 4 terminals, then you have 4 different terminal currents, and if you have only 2 terminals, then you will have just 2 terminals. Yes, this is quite easy to understand. For example, if you have terminal number 1 and terminal number 2, then how can you label these terminal currents? Then yes, you can write down terminal I1 for terminal 1 and I2. You can easily make it. But what I wanted to say is, terminal current is a property of a terminal. So So here we have an ID, but you cannot define this ID in the channel. Here, what is ID? No, the terminal current is the current measured at the terminal. So it is now inspiring us that if terminal current is the current measured at a certain terminal, then maybe we have a more general quantity which can be defined everywhere. And terminal current is just a realization or an expression taken from that more generalized quantity. So from that point we can introduce a more generalized quantity called as current density. Please consider the unit of this terminal current. What is the unit of terminal current? This is given as just ampere, and terminal, not terminal current, current density itself is ampere per square centimeter. So they have different quantities or different units, and current density is defined on everywhere. Okay. So now let me just draw our usual diagram for MOSFET. For example, here you have a certain terminal contact called as a source, and another one called as a drain, and another one called as body. You have seen this kind of graph so many times. So in this case, when we say what is terminal current, drain current, source current, body current, you are now saying at this point and that point, no, that point. This is all related with terminal current. However, you can define also another quantities at a certain position everywhere inside this system, and this at everywhere you can define a quantity called as current density. Please, once again, terminal current is a number assigned to a terminal, and this is a scalar quantity, and current density having ampere per square centimeter, it is defined on everywhere, and also this is a vector quantity. So now we can define the current density, and actually it is difficult to find in the literature the current density because this contains too complicated information, but fortunately now we can see that there is one example of a current density. So I took it from a literature research paper, and here you are now looking at a transistor. What is it? Here you have your source contact, and here you have your drain contact. And where do you have gate? Yes, gate is located here and there. So simply speaking, this is a so-called double gate MOSFET. And you have applied, of course, you have applied certain positive voltage to your drain contact. Actually, electrons are moving from your source to drain. However, current density, as if electric field is reference to our positively charged particle, Also, current density is reference to our positively charged one. So this one shows just a movement, describe the movement of a positive charge. And although electrons are moving that way, from the viewpoint of a current, it is heading this way. And you can see that here we have a densely populated vector field, and here you can see there is weakly populated vector field. What does it mean? It does say that starting from your drain, your current, here you have a narrow channel, and here you have a wider drain. Then the part aligned to your channel, here you have strong flux, and the part not directly related to your channel, then there is a relatively weak flux. After that, all of this traffic or flow should be merged where? In that way. After that, once it escapes this channel region, and this is once again widespread over its wider source region. So now you can understand this kind of information can be obtained from the current density. Simply speaking, at each point, this point, that point, other points, how the electrons and holes are moving, how fast, how many, that effects are combined into only one quantity called as current density. This quantity is simply proportional to what? Proportional to the average number of our charge carrying particle and average velocity of our charge carrying particle. If there are many particles and they are moving fast, then we will have quite long line for our J vector, current density vector. If there are many electrons but their average velocity is just 0, then we will have just a vanishingly small current density vector. Okay, are you with me? Also, if we have, although we have a small number of electrons, but if each of them is moving extremely fast, then still we can have quite a manageable number of our value of our current density. Okay, so I just spent quite a long time about the importance of current density. Current density shows everywhere how many, actually it does not say how many electrons are there, but it just shows the combined effect of number of electrons and their average velocity. That is merged into this current density defined everywhere. So once you understand this J vector inside it, then you can fully understand the behavior of your electrical current. Then there is an important relation between current density and terminal current. I told you repeatedly many times, terminal current is just defined on terminal. Actually, it can be obtained from this current density by performing just surface integral. So you have, for example, you may have this kind of device structure, and let's say that here you have a certain terminal. This is your terminal. Then what you can do is just to integrate your current density only over this terminal region. When you make that kind of surface integration, then you will have a certain number, and following the convention you have to add minus sign. Why do you have minus sign? So please have a look at okay, so please have a look at this one. The minus sign is related with this one. You have a MOSFET, then current is now flowing in this way, and of course this is your drain and this is your source. Then how do you say what is the sign of your drain current? You say this is positive current. And how do you say the sign of your source current? In that case you say source current is negative and the magnitude is exactly the same, so they are cancelled out. Simply speaking, following our convention, always we say that incoming current is regarded as the positive current. So but when we just perform this integration will give us the escaping current. So that's the reason why we just invert its sign by adding negative sign in it. So by performing this one, every time we just calculate how much current is coming from the external world into the device through the terminal area. That is measured by this kind of thing. Okay, then sounds great, and it simply says that if we understand current density everywhere inside our system, our device, then by integrating this current density over terminal area, we can always get the terminal current. So that's the reason why we wanted to know what is J inside our system. We wanted to calculate J vector as a function of position. What is J at here? What is J at here? That is our ultimate question we wanted to ask to ourselves. Then, in order to do such kind of thing, we must first say, okay, we have to calculate J. Then how this J can be expressed as a function of our other terms. So let me just write down most general form when we have just electrons and holes inside our system. Maybe you feel that, okay, that's true, there are only electrons and holes in our system in usual cases, but please think about this one. In this class we have all students related with solid state devices. However, if we just slightly expand our scope, then there are some researchers who are working with some sensor devices. For example, they have some aqueous solution and just drop a few drops, and it contains very important biomedical information, and your device just takes the important ingredient in that solution and generate electrical signal. In that case, the charge carrying carrier is no longer electrons and holes. Sometimes there can be ions in our aqueous solution. However, right now I will just confine our interest to the solid state, electrons and holes. In that case, we can simply write down in that way. So electron carries negative charge and electron density and our electron velocity. Wow. And also we have hole carries positive Q and hole density and hole average velocity. This is nothing but I'm saying that current density is obtained from the sum of two contributions from electron gas and hole gas. That's it. Of course, you must understand this is not exactly valid even in our solid state device case, because here we have additional term. What is the additional term? The additional term is called as displacement current density, and it is written as, this term is written as time derivative of our displacement vector. So what is displacement vector? That is related with the electric field, you know it. But you know, that is related with the time derivative of displacement vector. So when we consider once again the steady state condition means that this kind of time derivative gives us just number 0. So at steady state condition we can for a while neglect this displacement term. Then in this special case we have some assumptions. Okay, there are only electrons and holes who are carrying charges, and we are considering the steady state. In this case we can just express the terminal current, the current density as a sum of electronic contribution and hole contribution. Wow, that's it. However, unfortunately, although we are saying that J is obtained from minus Q and V, but natural question is, what is N? How many electrons are there? Then what is V? How fast are they? These questions should be answered. In order to answer this question, we have spent quite a long time. For example, let's consider a homogeneous doped n-type semiconductor. Then can you answer how many electrons are there? Yes, you can. For example, if you just doped 10 to the 17 per cubic centimeter for your wafer, then you can say that the average electron density will be 10 to the 17 per cubic centimeter. So let's say that for simple case, not a device, complicated device, but simple case, you know electron density. Then next question is, what is the average electron velocity? That is the main thing we have to understand, and we have a partial answer to that question. What is the partial answer? The partial answer is today we just studied that. Okay, velocity is just proportional to the electric field, and its proportional coefficient is mobility. When we adopt this kind of thing, so let me just do it here. Then velocity can be written as minus times mu n and electric field. So when this kind of calculation is done, then we can say Q times mu n electric field. that will be the contribution from the electronic part. Okay, then please go to the whole part. Then how can you make a whole contribution? In this case, your whole velocity should be once again written as a function of electric field, but in this case you have positive mu p times E. As I told you before, we have a positive sign due to the polarity difference. So when all of them are combined once again, then you will have this second term coming from our whole contribution. So quite interestingly, although they means that electrons and holes have the opposite polarity, but their contribution to the current density have the same sign, because there are twice of inversion. They have different polarity and their movement is also different. However, we are considering the movement of a positive side, so negative twice, that contribute positively. So now you can see that this means that yes, this one is the expression for our current density. But why I'm saying this is a partial answer? It is only related with the drift mechanism. We have another mechanism to be considered in this course, so I think that we have only 3 minutes left, so we will discuss that one later. And for a while I will just cover some other things to be covered in this drift part. So simply speaking, I'm just covering these two expressions. So electron current density due to drift can be written in this way, and drift current density, whole current density, can be written as this form. So you have different mu n, mu p, and n, but they looks quite symmetric. And from that one, you can also get total resistivity given by resistivity is nothing but just the inverse of conductivity, and this is conductivity. You can easily understand that is simply J equal to our conductivity Q mu n n plus Q mu p p times electric field. So this is called as conductivity, and resistivity is just the inverse of it. And there is another one called sheet resistivity. So please note that this quantity is a property of a material itself. If you have a certain material, you can define resistivity. However, sheet resistivity is nothing solely related with material itself. It is kind of a certain system made from a material. And then now think about it this way. Let's say this direction is vapor's vertical direction. So now you have introduced certain dopant in that way. So this is deep inside your vapor, and this is quite close to your interface, and you have applied this kind of dopant distribution. Here you have so many dopants, so therefore you may have so many electrons, and into this deep position, then you have almost no dopants, therefore you have no electron error. And now you have this kind of system, and you apply certain voltage difference at this point and that point. So what will happen to your system? If you have applied a certain voltage difference, then of course there will be current conduction. There will be current conduction, and there will be also small current conduction. In a vertical sense, which one will be the most active part? You know that these steps will be most active because there exist so many electrons, and this one will not be very active. Sheet resistivity, just to consider overall effect of this kind of differences. Okay, so from the viewpoint of the top, here we have some moderate number of electrons and so many electrons and not that many electrons. But sheet resistivity does not make a distinction between these depth resolution. We just make an integration over all kinds of these depth-wise differences, and just to say that what happens if I just apply certain voltage difference between this point and that point, that is merged. So vertical direction is just gone by what? Integration. So you can see that, you can easily understand how can you express this sheet resistivity out of this vertical directional electron distribution or conductivity distribution. So I will give this one to your homework in next Wednesday. So please derive some expressions. Right now you don't have a homework, but Wednesday I will distribute to the next homework. Okay, so time is up, and thank you, and see you next Wednesday.